Now let's talk about the ALU, the arithmetic logic unit. So the ALU is really the brains of a processor, and it performs the kind of basic arithmetic and logic functions: addition, subtraction, and OR. So we can input a control signal, ALU control, and indicate what function we want to perform, because we have 4 functions in this case that we want to perform: add, subtract, and OR. We use 2 bits for ALU control. And we have a symbol here for an ALU that looks much like an adder, and we'll put the words ALU on that symbol. And so this is an n-bit ALU, and the result, depending on ALU control, will give us the addition, the subtraction, or the AND or OR of the 2 inputs A and B. So let's take an example. Let's perform A or B. So the control bits, we look at our table here that we've chosen. The control bits ALU control would be 1, 1, and then we'd get the result here would be the bitwise OR of A and B. So how do we build this? So let's build the ALU. So let's start with the OR operation. So here we have an OR gate, and want to put in our inputs A and B, and we'll put our N symbols here to say those are N bits. So really that's N 2 input AND gates, producing an N bit result, 1 out of each of the 2 input AND gates. Okay, well, so if that's all we were doing, we would tie that directly to, result, and would be done. But that's not all we want to do. So we can go ahead and put that into a multiplexer and say, okay, well, we may want to do multiple operations here. In fact, we do. And so we know that, let's go ahead and put our ALU control signal here. And so for the OR operation, we want that to be 1, 1. So here we go. So if the ALU control is 1, 1, then we get out the OR operation of A or B. Okay, so let's go ahead and do AND then. And let's see, that's the 1, 0 option for ALU control. It's our 2-bit control signal. Well, similar, we can now just put our AND gate here and pull off our signals A and B, and those are all n-bit buses again. Okay, so we've got those 2. Let's go jump up to do add. So let's say we want to do an add operation of A plus B, and that would be our 0, 0 option here. Okay, so A plus B, we'll put in our adder there. A plus B, and we'll feed in our A, and then we'll feed in B, and again, n-bit buses. Okay, well, that was pretty easy so far. So now we have this ALU that performs 3 functions: add, and OR operations. But we also wanted to do subtraction. So let's think about how we can do that. Well, we could put a subtractor in there, right? We could say, okay, well, here we'll add a subtractor in here for that one. But as we know, adders are expensive, right? They take a lot of hardware, especially if we want to do it fast. And so let's think about some other options. Well, we do have this adder here. We know an adder can perform subtraction if we feed in B bar and a 1 into the carry in input. So we could have a multiplexer here that says, well, sometimes I want B and sometimes I want B bar to be fed into this. And we can see that, well, add, subtract, what's the difference is this, the 0th bit of ALU control. So when that's a 1, we want to subtract. When it's a 1, if we feed in ALU control bit 0. And when it's a 0, we want to feed in just B as usual. And so we can take that ALU control bit 0 and also feed it into the carry in input of our adder. So when ALU control is 1, then we're going to perform subtraction because it will choose B bar and make carry in 1. And then we also feed this into our 0, 1 input of our multiplexer. And again, these are all n-bit buses as well. Okay, so that's the machine written drawing of that. So it looks pretty good. So we have our sum input here. That one's subtraction, 0, 1. When that is true, ALU control bit 0 is going to be a 1 equals 1. And we'll say, okay, well, choose B bar and make the carry into this to the adder a 1. So we get A plus a negative B, or the choose complement of B. Okay, so let's do our other example we had before. We want to perform A or B. We feed in 1, 1 into our ALU control. That's going to select, on the multiplexer, select the OR operation of A or B, and then feed that out to the result. Let's suppose we want to perform A plus B. Okay, well, we want to do addition. So we make ALU control 0, 0. All right, the multiplexer is going to pick that output, the output of the adder. And our ALU control sum 0, bit 0 is 0. So it says, okay, well, choose B to feed into the adder. And A is always fed into the other input of the adder. So A plus B, ALU control 0, so the carry in is also 0. So we get A plus B, and that's fed into our multiplexer, which selects that input, 0, 0 input, and feeds that to the result. And we get result equals A plus B. And we can also add some flags, some status flags to our ALU. And these indicate whether the result is negative. So we have an N flag, 0, whether the adder produces a carry out, and whether overflow occurred. So overflow, we're going to refer to, this is signed overflow. So this is for choose complement numbers. So choose complement overflow. Okay, so we're going to look at these 4 flags here, and we can add this output, ALU flags. And these are useful to, right, that the ALU just performs the operation. It doesn't give us information about, hey, did overflow actually occur? Or maybe I want to know if the result was 0. If I'm doing some kind of comparison, maybe I subtract them, and I want to see if the result is 0, and other types of operations. So how do we add these flags? Well, we have our ALU. This is our original circuit here, our ALU, and now we have this extra circuitry kind of off of that ALU to tell us, well, let's output these flags as well. So we have our overflow, carry, negative, and 0 flags. Let's look at those each individually. So the negative flag, this is probably the easiest one. If the result is negative, so if this output of the multiplexer is negative, well, we can tell that because the most significant bit, in this case for a 32-bit ALU, result sub bit 31 is a 1, and we can just make that, tie that to our negative output. So when the result is negative, N will be 1, and we can tell that result, the output of the ALU is negative. Okay, let's look at the next one. So we also have the 0 flag. So we want z to be equal to 1 if all the bits of result are 0. Well, how do we do that? Well, it's not, right? Result bit 0, if that's a 0, so that bar, and result bit 1 bar, and result bit 2 bar, blah, 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 blah. And so we have this. What kind of gate is that? People often think that's a NAND gate. That's actually a NOR gate, right? Remember that this gate, push those bubbles through, and we're going to get kind of more typical or easily recognizable. I take those two bubbles, push them to the output. The body of the gate changes to an OR, and we get a bubble on the output. That's our NOR gate. Okay, but in this case, it's easier to draw it this way and easier to think about. Well, we want all the bits to be 0. So we're detecting result sub 0 bar and result sub 1 bar and blah, 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 up to results of 31 bar. If those are all 0, then we output the 0 flag. Okay, so the next status flag is the carry flag. So this is, we want to know, hey, if carry out is a 1, and if it's performing addition, then or subtraction, we want to know if carry out was a 1. So how do we tell if it's addition or subtraction? Well, remember from our table here, addition and subtraction, this bit ALU control sub 1, ALU control bit 1 is equal to a 0 when the ALU is performing addition or subtraction. And so if that's happening, we put ALU control bit 1 into inverter. This tells us, hey, it's adding or subtracting. And now I care about what the carry out is. So if that's true, if it's adding or subtracting and carry out is 1, we want to output this carry flag and make that carry flag 1. The last flag is the most complex one, saved it for last. So is the overflow status flag. And this is for adding two numbers, two 2's complement numbers or signed numbers, right? We refer to 2's complement numbers generally as just signed numbers. Okay, so phi is going to be 1 if the addition of, so there's several conditions here. So the addition of two same sign numbers that produces a result with opposite sign, right? So we're adding two positive numbers, we get a negative result, or we're adding two negative numbers and get a positive result. So first of all, we have to know, are we adding two numbers with the same sign? So that's the only possibility where it possibly could get overflow. And the result is the opposite sign. Okay, so let's take a look at this circuit more closely. So overflow is going to be 1 if, well, first of all, we have to know if it's doing an addition or subtraction to start with. So that ALU control bit 1 is going to be 0. Remember, we have 0, 0, 0, 1. For addition, it's 0, 0, and subtraction, it's 0, 1. So this bit, this most significant bit of ALU control is 0. So we say, hey, was that ALU control bit 1, 0? So we invert it and say, yep. If that's a 1, then we know, hey, we're doing an addition or a subtraction. So we need to detect for overflow. We're not going to detect for overflow if the ALU is performing or an AND operation. Okay, so first of all, is it performing addition or subtraction? Next condition is, do A and sum have the opposite sign? Okay, so we're going to say, we just pick one of them. It could be B or sum have the opposite sign, but we, in this case, just pick A, bit 31, XOR sum bit 31, right? If they're the opposite sign, remember the the XOR function is going to output a 1 if they're the opposite. So 0, 1, 1, 0. Another way of thinking about XOR, right? If A and B have the opposite value, A is 0, B is 1, or A is 1, B is 0, then that outputs a 1. So that tells us, hey, are they opposite? Are they different? So A XOR sum 30-bit 31. And A and B have the same signs for addition, or A and B have different signs for subtraction. Okay, so that's this last part, this last gate here tells us, okay, if ALU control bit 0, remember that's for addition, equals addition, we want to know, hey, do these have the same signs? Right, if they're addition, let's do an example. Let's suppose they're 1, 1. That does have the same sign. We get the XNOR of 1, 1, 0, 1, 1, and ALU control, in this case for an addition, is going to be 0. It's going to say, okay, well, the XNOR of 1, XNOR 1, XNOR 0. Remember, XNOR outputs a 1 if an even number of inputs is 1. And so this says, yep, they do have the same sign. So there's a possibility that we're going to get overflow. Okay, let's do the other case where, let's suppose it's doing subtraction. 0, 1 is subtraction. So we get a 1 here. And now we care if they have opposite signs. So if they have opposite signs, 0 minus a negative number is going to be basically like adding two positive numbers, so possibility of overflow. And so we're going to get the same thing here, 1 XOR 0, XOR 1. We have two 1s in that XNOR gate. 1 XNOR 0, XNOR 1. We have two 1s in that XNOR gate, so we're going to get a 1 output saying, oh, it's possibility of overflow. So let's recap that again. So here's a case, for example, where we're doing subtraction, and let's say they're the same sign, positive minus a positive. There's no way to get overflow. That's like adding a positive and negative number. Right here we only have a single 1. So we have 1 XNOR 0, XNOR 0. I'm going to say, hey, no possibility of getting overflow. So it's going to say, hey, just ignore these 0 and whatever. It's going to say there's no possibility. There's no way to get overflow. Okay, so overflow is going to be 1 if the ALU is performing addition. That's this case here. So this tells us addition or subtraction. That's that wire there. And A and sum have the opposite signs. That's this wire here. And let's do that a different color here. And either A and B have the same sign for addition. ALU controls 0. ALU controls bit 0 is 0. Or A and B have different signs for subtraction. And that's our final XNOR gate here that tells us that. So if, for example, not doing an addition or subtraction, ALU control bit 1 is a 1, so it's doing an AND or an OR operation. This one says, hey, you know, I'm not going to get overflow, right? Because this is a 1, either the 1, 0 or 1, 1 case for ALU control, not going to happen, right? It says 0, not going to even detect for overflow. Okay, so let's say it is performing an addition or subtraction, so we get a 0 on this, 0, 0, or 0, 1 for ALU control, and we get that inverted, and says, hey, a possibility of overflow here. Okay, this is a 1, and it says, hey, yeah, the operands and the sum, really just A and the sum, have opposite signs. A bit 31 XOR sum. But maybe we're doing addition and A and B have opposite signs. Okay, this one says, not going to happen. Or we're doing subtraction and they have the same sign, says, not going to happen. But if all of those are true, right, we're doing addition and subtraction, yes, the sum and the operands have opposite signs, and we're adding and the operands have the same sign, or subtracting and they have different signs. Yep, then we have 1 and 1 and 1, overflow. So all of those conditions have to be true in order to get overflow. So here's our complete ALU with status flags. Again, our ALU here on the right and our status flag circuitry on the left. So we can also use these status flags to compare numbers. We first subtract the numbers, so we perform A minus B, and then we look at the flags to do the comparison. So after performing A minus B, if the 0 flag is asserted, so the result was all zeros, then whether signed or unsigned, whether we're dealing with signed or unsigned numbers for A and B, they are equal. So if the 0 flag is 1, after we subtracted A and B are equal. And then we just invert the 0 flag to say whether they were not equal for both signed and unsigned. Now, for less than comparison, it's different for signed and unsigned numbers. So we actually introduced less than comparison for signed numbers in the earlier slide, and we said, well, just look at the most significant bit to see if the result's negative after you subtract them, then A is less than B, right? A minus B, if A is less than B, when we subtract them, we'll get a negative result, 2 minus 3, it's gonna be minus 1. Yep, A is less than B. But we said to watch out for overflow. And so, in fact, that's how we take care of if overflow occurs, then we have to XOR it with a negative flag to tell us whether A is less than B. So let's do an example here. Let's suppose A, so we're going to perform A minus B, trying to tell if A is less than B. Let's make A, we'll do 4-bit comparisons. Let's suppose A is minus 8 and B is 1 or something. And so we know we're going to get overflow with 4 bits. Minus 8 minus 1 is going to give us minus 9. We know that doesn't fit in 4 bits. So let's see what happens. So minus 8 is 1, 0, 0, 0. There's our minus 8. And we're performing minus B. B is 1. So minus a plus a negative 1. So this is performing A minus B. So minus 8 minus 1. We're going to add those together. We get 1, 1, 1, 0, carry the 1. Okay, so remember with signed numbers, that carry out of the most significant bit means absolutely nothing. We detect overflow by saying, oh, hey, did I have 2 operands with the same sign, and did the result have an opposite sign? Yes, in fact, it did, right? We're adding 2 negative numbers, minus 8 and minus 1, and we got a positive result. So overflow occurred in this case, and the negative flag, that most significant bit, is 0. So if we XOR those together, and XOR overflow, we get 1 XOR 0 equals 1. In fact, A is less than B, which is exactly what we wanted, right? Minus 8 is less than 1. Check. So in order to compensate for overflow, we have to XOR the negative flag with our overflow flag. For unsigned addition or unsigned comparison, less than comparison, we look at the carry out of that most significant bit. And so we're going to say when there's no carry out, A is less than B. So let's look at this. So A less than B. Now we're doing interpreting these numbers as unsigned numbers. So let's say A is 8 or something. So A is 8 and B is let's 9 or 10. Let's make B 10. So 8, is it less than 10? Yes, it is. So we expect to get this. We expect to have a no carry out of that most significant bit so that we get a 1 to say, yep, A is less than B. So let's see what happens. So A less than B, we're still performing A minus B. So we're going to get A, there's A, or 8, minus B. So we still take that B and take the 2's complement of it, invert the bits, add 1. And we're going to get 1 plus 1 is 0, carry the 1, 1, 1, 0. So we're going to get 0, 1, 1, 0. All right, that sounds good. And so we're going to now do this. And we will get 0, 0 plus 1, 1, 1, 1. And notice that there's no carry out of that most significant bit. So C is 0, and we get not C to tell us whether A is less than B. So not C, since C is 0, this carry out of the most significant bit, or the carry flag, is going to be 0. Overflow, or less than comparison is A less than B. Equals not C equals 1. Okay, so different for unsigned and signed numbers for less than comparison, and we've also now taken care of what happens when overflow occurs. So now we have our signed and unsigned less than comparison. Well, greater, less than or equal to. Actually, let's do the opposite of that. So we have less than here. The opposite of that is greater than or equal to. Okay, well, let's just put a bar over this, right? N XOR V bar will give us the opposite case. It's not less than, in fact, it's greater than or equal to. And same thing here, we put a bar over this. C bar with a bar over it is just C, involution. And now let's look at the next case, less than or equal to. Well, we already took care of less than. Here's the less than case. Or equal to, we have the equal to case here. So we OR that, less than or equal to. And same thing for unsigned, less than or equal to. And now greater than is going to be the opposite, right? These have the inverse relationship, less than or equal to, and greater than have the inverse relationship, right? If it's not less than or equal to, it means that they're greater, they have a greater than relationship, right? If A is not less than or equal to B, it means that A is greater than B. And so we take this and we invert it. So we get Z or N X or V, and we invert that. And then we can do De Morgan's on that and say, okay, well, turn that OR into an AND, bring down the terms, and then invert them. And we get not Z and not N XOR V, or the XNOR of N and V. Okay, but the easiest way to think about that is this is just, right, we just put a bar over that, the inverse of that. And same thing here, put a bar over that, and we get greater than, like whether A is greater than B. And so Z or C bar, well, that would be less than or equal to, so we want greater than. We invert that, perform De Morgan's, that OR turns into an AND, bring down the terms, and then put the bar over each of the terms, and we get not C and C. We can also expand our ALU to perform other operations such as set if less than, or SLT. This operation sets the least significant bit of the result if A is less than B, and otherwise it's 0. So if A is less than B, the result will be all zeros and a 1. Otherwise, the result will be 0. We could also expand it to perform the NOT function and the XOR function.